And to kick this off, we have an invited talk from Anya Nugent, who's a postdoctoral fellow at Harvard CFA, who's going to talk to us about utilizing the power of host galaxies to discover transients with Roman.
Hi, everyone. Thanks for joining us at 9 a.m. to talk all about explosive transients. I'd like to thank the organizers for inviting me to give this talk on how we can use transient host galaxies with Roman to discover transients and understand their progenitors. All right, so to start us off, Roman is really going to transform extragalactic transient astronomy through repeatedly imaging the same field, which is going to allow us to find things that are changing in the night sky, a lot of which will be extragalactic transients, or at least that's what I am most concerned with. Now, there's a ton of different surveys that Roman will be doing that are going to be taking multiple epochs of those same fields. Jacob Jensen will be talking a little bit more about that in the next talk, so please see him. Today, I will really just be talking and focusing on one of the main surveys that Roman will be doing, which is the High Latitude Time Domain Survey. And this is really going to be Roman's powerhouse in extragalactic transient discovery. So HLTDS will be focusing on 3 different fields in the night sky. One northern field, which is the Elais N1 field, and then 2 southern fields. These are both Euclid deep fields. It's about 18 square degrees in total, and I believe the reason that these fields were chosen was because they're far enough off the galactic plane that it will allow us to find extragalactic transients. And these have a ton of pre-imaging from different surveys, so we tend to know these fields pretty well. So what's really cool about HLTDS is it's going to be imaging those parts of the sky every 5 nights for for 2 years. And this survey, this main survey, is planned to occur within the mid 2 years of Roman's mission. Now, before and after that core component, there will be a pilot and extended survey. These will be somewhat similar, however, they'll have a longer cadence between epochs, but they still should give us enough information on new transient discoveries. Now, what's really cool about that 5-day cadence is that's not only going to allow us to discover transients that are happening in those fields, but also help us build light curves of those transients. And that is really important information for us to properly photometrically classify those events. Now, beyond that, there are plans to take spectroscopic observations with the PRISM spectrograph in these fields too, I think on a similar 5-day cadence. Those will mainly be following up things that look like type 1a supernova, but hopefully we serendipitously get other kinds of transients in those fields, spectroscopic redshifts of their host galaxies, so we will have a lot of information on transients with Roman in the next few years. Now, what's really cool about Roman is it's a highly sensitive instrument. So this is going to allow us to get very, very faint transients down to 26th, 27th magnitude in the main HLTDS survey, which we can see here. Now, when we compare to other well-known surveys like ZTF and Rubin, we see that that is far deeper than what those 2 surveys are capable of. So not only is this going to allow us to get fainter transients, but because Roman is centered on those near-infrared wavelengths, that's going to be especially useful for getting high redshift transients where their optical light has been pushed off into those NAR wavelengths. Now, there's another survey which Lin Yan will be talking about a few talks from now called RISE, which is going to be stacking images from surveys that have multiple epochs. It's called RISE, and that should get even deeper than the main HLTDS survey, which will be really cool. So to give you an idea of what the redshift distributions for many of our well-known transient populations look like, I'm showing these plots. These are from the Hourglass simulation, which was simulating what HLTDS transients should look like. And what you'll see here is that for many of our well-known transients, like our type 1a supernova, our core collapse supernova, it is predicted that the majority of transients that Roman will discover will be beyond redshift 1. And we should also get a handful of very rare transients up at high redshift 2. Now, I will note that the Hourglass simulation only simulated transients up to about redshift 3, but for some of these transient classes, given how bright they are, you should be able to see them even further beyond redshift 3. So the Roman is predicted, or HLTDS in total is predicted to give us around 100,000 transients in total. Now that number might not seem as impressive as what we're gonna soon be discovering with Rubin's LSST, which just began, I think, a week ago. But it's really the redshift range that Roman will give us that is going to be far more impressive than what is currently possible with Rubin and ZTF. So here we're looking at those same different transient populations, what Roman should get and what Rubin is expected to get as well. And you'll see that for Rubin, while most of these type 1a supernova, core collapse supernova are only going to be discovered out to about a redshift 1, once again, the majority of Roman transients will be discovered beyond redshift 1. Which is going to be really impressive, and this in total is going to give us a lot of understanding on how these different transient types evolve over cosmic time. So why is this so cool? So redshift greater than 1 might not seem like that high or that impressive if you do galaxy science, if you do AGN studies, which can frequently be detected beyond redshift 1, but this is a relatively new field and pretty uncharted territory in transient science. So far, we only have around 100 or so transients that have been discovered beyond redshift 1, and even less so that are spectroscopically classified. So Roman really will be transforming the way that we understand transients, especially in the high redshift universe. Now, many of these transients were discovered through JWST-based Galaxies surveys. So I'm showing 2 examples here. We have JADES on the left and Cosmos Web on the right. So these are multi-epoch JWST Galaxy surveys, where basically these teams went in and they were able to do difference imaging and find transients that were occurring in those fields, associate them to host galaxies, and for most of these get a photometric redshift to understand the redshift that those transients were occurring at. Now, at least for the JADES sample, the epochs were taken a year apart, and the majority of transients were only detected in a single epoch. So that is not enough information for us to determine what kind of transient it was, or even distinguish between things like AGN and TDEs and supernova. So I think what these studies have really highlighted is the difficulty in characterizing and classifying these high redshift transient populations. Now, Roman, of course, is going to help a lot with that because it has a 5-day cadence in the HLTDS survey, so this should be able to give us light curves for many of our transient populations. However, we're still going to be confronting similar issues in that a lot of the transients that Roman will be discovering are going to be very faint. They're going to have very noisy photometric data sets, and a 5-day cadence, even though that's faster than what's observed in these JWST targeted surveys, that's still long. Even Rubin's 3-day cadence is fairly long for transient astronomy, and we'll be missing a lot of information with that longer cadence. So I think this huge question remains of how do we actually go about classifying transients with limited photometric data? How do we get most out of this Roman era to build up our transient populations and do all the science that we're trying to do? And what I will try to argue to you today is that using host galaxies is the best way to do this. And why is that? Well, host galaxies have really been key in the past in distinguishing different transient types and understanding their progenitors at low redshift. So we can assume that the same probably stays true as we extend into further redshift. So what I'm showing you here is a bunch of different supernova host galaxy populations and how they're tracing specific star formation rate, which is star formation rate divided by stellar mass, and stellar mass. We obviously have 2D distributions up at the top, 1D distributions at the bottom. In the 2D distributions, that black dashed line just represents a star-forming main sequence, which is where star-forming galaxies move along as they gain in stellar mass until eventually they're no longer star-forming and they fall off it. Now, without even knowing what each of these different kinds of supernova represent, we can clearly see in both the 2D and the 1D plots that how they trace star formation and stellar mass is very different between those supernova classes. And this all relates to their progenitor formation pathways and timescales. So to bring up one example over here, Type 1a supernova, which come from the thermonuclear detonation of a white dwarf. White dwarfs, compact objects, it takes a long time to form a compact object, takes a long time to detonate that white dwarf. Because of that, they have longer formation timescales. We would also expect these to occur in galaxies that are more evolved, so they have higher stellar mass, lower star formation rates, and in fact that we do see that type 1a supernova have a higher density of host galaxies in that low star formation rate, higher stellar mass region, especially when we compare that to our core collapse supernova host galaxy populations, which are the 3 plots on the right. Now you may also be able to see some subtle differences between the star formation rates and stellar masses between our core collapse populations. I do actually think this becomes more obvious when we look at other host galaxy properties like metallicity, which I'm showing over here. So all of these transients on both of these plots over here have been connected to having very young, massive stellar progenitors. But as we can clearly see, even though these are all coming from similar-ish objects, how they trace metallicity is very different between these populations. Once again, this relates to exactly the kind of star that's exploding in each of these cases. So to highlight a few examples, we see that 1BC supernova, which is our stripped envelope supernova, this coming from the stars that have lost their outer hydrogen and helium envelopes, tend to be occurring in host galaxies that have higher stellar mass and higher metallicity than the type 2 supernova, which are coming from the stars that have retained that outer hydrogen envelope. Now it is thought that the reason for this is that there are stronger winds or stellar winds at higher metallicity that can push out those outer envelopes, which is why we see this distinction. But I think what I really want to highlight here is that's information that we get directly from the host galaxies. But it's also a very distinguishing trait between 1BC and type 2 supernova. Now, another thing that I would point out over here is that we see that superluminous supernova have the lowest metallicity out of all of these different transient populations. Now, superluminous supernova are thought to be coming from the most massive stars, or some of the most massive stars in the universe, which we would typically expect to find in very low metallicity environments. And that also becomes obvious when we look at their star formation rates and stellar masses in comparison to normal field galaxy populations. So what's cool is because superluminous supernova are so bright, they're actually one of the only transients that we can currently detect out to high redshifts in surveys like Rubin and ZTF. And what's very cool is that we see at both low redshift and at high redshift, superluminous supernova seem to be occurring in very extreme environments compared to the general field galaxy population, which is shown in that gray-black histogram in the background. Now that is information that we can use to discover superluminous supernova in the future, just by looking at host galaxy properties and noticing that maybe a bright transient has occurred in an extreme environment might be indicative of one of these extreme supernova. Okay, so cool. Hopefully now we have a baseline for understanding that host galaxies are helpful in distinguishing these different transient types and understanding what their progenitors actually are. So how can we actually use host galaxy properties in early transient classification? So I think an obvious thing that host galaxies give us is redshift estimates. So we know that host galaxies will be there well before the transient happens, they'll be there well after the transient has faded, and especially when we're thinking about Roman and the HLTDS fields, many of those fields have had imaging before, so we already probably know the host galaxies that many of those transients will be occurring in already. So we can use those to get a photometric redshift estimate, which is going to give us an idea of what that transient luminosity is. So I'm sure many of you guys have seen a plot similar to this before, but here we're just looking at the peak absolute magnitude, so how bright the transient gets in comparison to how long it stays above half peak brightness. And you'll see here that all these different transient types have very different peak luminosities. So simply by getting a rough photo-Z estimate, we can begin to put transients on this plot and get a better indication of what actually that transient was. just with one detection and using a photo-Z. All right, so host properties have also been used, or other host properties like stellar mass and star formation rate, which we were seeing before, are very useful other properties in distinguishing these transient types. Those have actually also been used in machine learning-based classifiers to photometrically classify different transients. So I have a bunch of different codes over here that do this, or papers that have looked into this. I'm just going to highlight one. This is called SPLASH. This is written by Adam Boesky, who is a soon-to-be grad student at Harvard. And what SPLASH basically does is it gets an alert that the transient has occurred. It looks into pan stars, and it associates that transient with a host galaxy and pulls a photometric or spectroscopic redshift of that host from pan stars. It then pulls a photometry from pan stars. It estimates a mass and star formation rate very quickly, and then uses that information to understand what kind of transient or supernova that was. And you'll see here in the confusion matrix that SPLASH actually does a very good job at distinguishing between type 1a supernova and core collapse supernova. And this is without using any information on the transient itself. There's no light curve information, there's no luminosity estimate of the transient. This is purely looking at redshift, mass, and star formation rate of that host galaxy to understand what that transient could have been. So this is something that I think is really useful, especially when we don't have a lot of transient information or when we're waiting 5 days for the next epoch of Roman data to come in. So another way that we can use hosts, or the final way that I think that we should really be using hosts, is to get an estimate of line of sight extinction, because we know that transients will appear redder in dustier environments. And we actually saw evidence of this when looking at the host galaxy properties of a type 1bc spectroscopically classified and photometrically classified sample. And what we noticed when we were looking in our photometrically classified sample of type 1bc hosts is that there were all these hosts in this region over here that had high star formation rate, high stellar mass, and were very, very dusty. And we did not see the same thing occurring in our spectroscopically classified sample, but we did see that something looks similar in our type 1a supernova host galaxy sample. So that flagged us as like maybe something weird is going on here. Let's take a deeper look at these supernova and see what's going on. And what we actually found is by looking at their light curves is those did actually just look like severely red in type 1a supernova. So dust is definitely something that we want to be correcting for, and information that we get directly from the host galaxies. Okay. All right, so now we know how to use host galaxy properties, what tools are actually available to us to be able to rapidly determine host properties like photo-Z's, mass, star formation rate, and dust for Roman transients. We want this to be happening on a rapid time scale because we want to be able to use this in real time for classification purposes. So we have a ton of photometric redshift tools that are currently available to us. I'm bringing up Rail over here, which is a Python package that basically inputs a ton of different photo-Z codes into it. And instead of you having to individually go through and learn all the commands to run these codes, it has a very self-consistent way that you can use all these different models. So you do not need to be a photo-Z expert to be able to use Rail or any of the photo-Z codes that it has implemented. So Rail contains a bunch of different types of photo-Z tools. Some of these are machine learning-based algorithms. There's others like BPZ and LaFair that are more template-based. And actually this past week, we were working with the Roman Rapid team to think about how we might be able to implement some of these algorithms into the Roman transient alert pipeline, as we know how useful simply getting a redshift estimate might be for understanding which transients might be of high interest to the community. So also in this past week, we did a lot of testing with these different photo-Z codes to determine what might be the most useful given the data that we expect to have when Roman launches. And so here's just performance of all of these different photo-Z codes that we tested out using open universe Roman and Rubin data. And what's exciting is that most of these PhotoZ codes are showing very well constrained PhotoZs, some a little bit better than others. That probably has to do with the algorithm, the training set data that we're using, everything in there. And why we wanted to test with optical photometry is because we know that we should have a lot of optical or supplemental optical photometry in those Roman fields. Okay, so let's say you're not just interested in PhotoZs, you want something beyond that, you want your mass star formation rate dust measurements. Well, I can introduce to you Frankenblast, which is our rapid transient host galaxy tool. And if you're familiar with the BLAST web application, Frankenblast is based off of that. So what does Frankenblast actually do? So at first, once it gets a transient, it does a host galaxy association using this code called PROST. I don't have a ton of time today to get into what PROST actually is, but it basically uses a directional light radius method to be able to determine what the true host is. It then, the first version of Frankenblast, does aperture photometry on the host galaxy, pulling archival images of the field from a variety of surveys, including Galaxies, Pan-STARRS, Decals, 2MASS, and WISE. And then after that, it runs a very rapid host galaxy SED fit with this thing called SBI++. I'll get into what that is in a second, to obtain estimates on stellar mass, star formation rate, dust, age, anything else you're interested in. And what's really cool is that it can complete all of these steps in less than 15 minutes for a transient. Another thing that I want to point out, and I'll get into this a little bit more in a few minutes, is that we are actively developing versions of Frankenblast for Roman and Rubin data because we want this to be used in transient classification and for understanding those host populations in these surveys. Okay, so very briefly, what is this SBI++ thing that I brought up, and how is it different than other SED fitting tools? Well, SBI stands for Simulation-Based Inference, which basically, this uses normalizing flows to learn posterior density distributions of the stellar population properties of interest directly from simulated photometry. So you basically create a simulated training data set where you have photometry, you have the stellar population properties that that photometry refers to, and SBI will basically learn how we go from the photometry and noise on the photometry to posterior distributions on all of those different stellar population properties. So what is the plus here? Well, baseline SBI, it assumes that the data that you're testing it on looks exactly like what's in your training data set, but we know that some galaxies, they might not be detected in some filters, they might have noisier photometry than what we expect, and so the plus here just really means that it can handle noisy and missing observations. Now, SBI++ was originally developed to study the galaxy properties of a bunch of galaxies in a JWST-based survey, and they compared this to more traditional SED fitting tools that use nested sampling instead of machine learning-based algorithm to build up those posterior distributions. And what they noticed is that SBI performed just as well as those other methods, but in a fraction of the time. So once again, SBI takes 5 to 10 minutes to run. Nested sampling can take hours to days, depending on the complexity of your model. So we actually also tested this out based on our initial algorithm that we did using all of those archival Pan-STARRS, Decals, that data set. And we compared it to Prospector, which is a stellar population modeling algorithm that uses nested sampling to see how well those actually did perform against each other. And what we noticed was quite interesting. We tended to find that SBI had larger error bars on a bunch of different stellar population properties, but within those error bars, they were getting, for example, the true redshift of the host galaxy, whereas methods that use nested sampling, they tended to have very small error bars on a very incorrect, for example, redshift. So in turn, that meant that, if we're getting a bad redshift estimate, we're also getting a very bad mass estimate because geez, I'm running out of time, because that's a redshift-dependent parameter. All right, let's see. So I will just briefly bring up that we have a Roman Cycle 1 proposal to basically take Frankenblast and these PhotoZ tools and publicize them in real time for Roman transients and Rubin transients that are discovered in Roman fields, because we know how useful this information will be for classifying transients in the future. So I'm just showing a screenshot of the BLAST web application. Our idea is to build something that's somewhat similar to that. However, because this was just funded, I'm really open to hearing the community's thoughts on what you would like to see on this website. And in the last few seconds, I'll just say the point of this is for us to be able to discover these extreme transients like superluminous supernova, like para-instability supernova, and then finally also to really study how transients and their host galaxy environments evolve over cosmic time. So with that, I will leave my concluding slide up. Thank you very much.
All right, thanks Anya for the really nice talk. Questions for Anya? Okay, how about right here, right up front?
Do the parameters of this survey mean that there'll be 36 data points on each light curve at the end of the survey?
For all transients?
For all objects?
36 data points.
Well, I'm dividing 180 by 5.
Okay.
Parameters.
I think it will depend on the kind of transient. I'm not sure. I think, yeah.
In transients, every object
Oh, yeah.
will be photometered 36 times in the survey, is that right?
I know, I think it should be more than that. Yeah. Yeah.
All right, more questions for Anya. Gabrielle in the back. Yep. Sorry, you're on.
Thank you, Anya, for the very nice presentation. So I do understand the effect of the plus in SVI++.
Yeah.
Now you can handle with noisy data and out of training distribution data.
Yeah.
That's okay, but could you please expand a little bit more on the heavy machinery behind the plus? What's happening in this plus so it can handle noise data?
That's a great question. It's just simply a nearest neighbor search. So it's just looking for SEDs within your training set data that look similar enough to your observed SED. And then it's saying, okay, I'm missing this band, or this one band looks a little bit noisy. When I look at similar SEDs, what does typical photometry at that point look like? And then it's just emceeing over that to get an estimate of like what that photometry should be. So that's not super ML based, but like the rest of the normalizing flows and actually getting the posterior distributions is.
It's simple but very smart. Nice.
Yeah.
Thank you.
Oh, over here.
Thank you for the very nice talk. I just have a question about like, when you go really deep, for example, when we're searching for transient using GWST data, there are some cases where you find a transient and there is a nearby galaxy, but the transient is not necessarily associated to the galaxy, right? It could be a hostless transient in the background.
Right.
And also we have cases where you have one transient and there are multiple host galaxy, multiple galaxies. And I'm just wondering how the code deal with that.
Okay, well, thanks for bringing that up, because then I can go back and I can talk a little bit more about what PROST actually does. So PROST is really cool. Oops, I think I went too far. PROST is really cool because it actually accounts for a ton of cases like that. So it will look into your field and it will actually give you a probability that this transient is hostless, or that your images don't actually go deep enough for you to obtain the true host. And so if that number is high enough, maybe you say, okay, my host association or the brighter galaxy that it actually associated to is probably not the true one. But then this cool directional light radius method, it also goes in and it looks at the full like extendedness of the galaxies nearby. And because we know that supernova can be offset from the center of their host galaxies, maybe off in a spiral arm or something like that, it'll take that information into account and give you a better indication of what the true host is. But then of course there are cases where maybe you have, you know, like a galaxy, a pair that's occurring at the same redshift and your transients right in between them, and it's just really difficult to say at that point which one it was truly coming from. But like that is also information that you get out of using something like PROST.
Okay, I might take the last question. So yesterday we heard about this Roman Extreme Deep Field survey. I'm wondering if you have any thoughts about how that might compare to the results from HLTDS. And we just heard about it yesterday.
Yeah,
so
oh my
I'm
gosh,
curious.
I would need to think about it a little
No
bit more,
problem.
but that sounds really cool, at least just like with the depths of getting deeper imaging in those fields and, you know, fainter galaxies, potentially fainter transients there too. Would be interesting, yeah.
Yeah, sounds good. All right, let's thank Anya again.